Hello everyone, my name is Deepak Singh. Today I will take you through the research paper titled User-Oriented Fairness in Recommendation System. So, in recent years, recommendation systems have been very much integral to various online platforms like Amazon, streaming services like Netflix, Prime, and social media. These systems aims to provide a personalized content and product suggestions, optimizing for user suggestion. However, a major concern is that these algorithms may exhibit biased treatment towards certain user groups, which may lead to unfair or unequal user experiences. Fairness and recommendation system, particularly from the research user-oriented perspective, is an area of research, and we are going to explore this in in the subsequent slides. Recommendation systems have a very crucial and important role to play in various online platforms like Amazon and social media. Their main business model is based on how many users they are keeping engaged at a particular time. But the problem with this type of things is that active users who are consuming more content or buying more items have a better set of recommendations compared to inactive users. So inactive users might have poor biases or get poor recommendations. So our study addresses this issue from a user-oriented perspective. Basically, we are doing a re-ranking recommend. Basically, we are doing re-ranking on recommendations so that we can reduce the bias which is present between active and inactive users. The increasing reliance on recommendation system in digital platform has revealed biases in traditional recommendation model. Specifically, active users on system receive better and good set of recommendations compared to their counterparts. Because of which, what happened that disadvantaged users don't get good recommendations, which may lead to reduction in the satisfaction and they might engage less on these websites. So this in this problem statement, we are going to explore the concept of user-oriented fairness, which seeks to mitigate the biases that affect different groups of users based on their activity levels. Traditional models often optimize recommendations solely based on accuracy, neglecting the fairness consideration. In this context, the user-oriented fairness addresses this bias by ensuring that the recommendation quality is balanced across users with different activity levels. Rather than just focusing solely on overall accuracy, we are focusing more on fairness considerations. So let's go through our experimental setup. To ensure fairness, we define a metric called epsilon fairness, which measures the quality difference present between the recommendation for active and inactive users. The difference is within an acceptable threshold, which we have called epsilon. The system is considered to be fair. Our solution minimizes the disparity using a re-ranking algorithm that optimizes the recommendation for inactive users. Keeping one thing in mind that the active users' performance doesn't decrease drastically. So apart from this, we are storing results in the results folder for doing analysis. So talking about datasets, we have used the Amazon datasets for beauty products, grocery products, and health products. And we have divided these datasets into advantage groups and disadvantage groups based on their activity level. So now the next thing is that how we are calculating activity level. So basically we are using three set of parameters for calculating the activity level. First one is the total number of interaction that they do with the website. Second one is sum of the price of product that they have purchased from the website. And third one is the price of the most expensive product they have bought from the website. So on the basis of these three parameters, we are going to classify the users. So now coming to the classification, the top 5% of active users are classified as advantage group and the remaining 95% are classified as disadvantaged groups. So yeah, in this way, we are classifying the users in two categories. So to evaluate our fairness adjustment algorithm, we have used two evaluation matrices. First one is NDCG. So this matrix evaluates the relevance and the ranking quality of items within the top 10 recommendations, awarding higher score where relevant items appear in higher positions. On the other hand, the second is F1 score. This matrix calculates the harmonic mean of precision and recall within the top 10 recommendations, providing a balanced measure of accuracy that reflects both the relevance of recommendation items and the proportion of relevance item among the top 10, that is precision. Higher F1 score indicates better performance in returning relevant items within the top rank recommendation. So yeah, so in these two graphs, we can see the F1 and NDCG score before and after applying a fairness adjustment algorithms. We can clearly see that the scores are higher for active users and less for inactive users before applying any sort of fairness adjustment. But after applying, we can see that the F1 score have decreased for active user and it has increased for inactive users. And we can control the difference between them by adjusting the epsilon parameter. And we will see more about this in upcoming slides. As seen in the previous figure, we can see that before optimization, F1 and NDCG score of inactive users was less compared to active users, and overall score was close to inactive users because they are higher in proportion. Re-ranking algorithm, what it does that it picks the top 10 recommendation for the user and solve the optimization problem to satisfy the given epsilon constraint. In this scenario, we have kept the epsilon value as 0 and obtained the result. Keeping the epsilon value as 0 means that we aim to make the recommendation quality of both inactive and active user equal. That is, difference allowed in active and inactive is close to 0. That's why we can see that after optimization in the previous figure, the score of the active and inactive users were equal. But the main issue here is that when the re-ranking algorithm increases the recommendation score of inactive users, but drastically decreases the recommendation score of active user, which is not desirable at all. Our aim is to increase the recommendation score of inactive user, but not at the cost of decreasing the score of active users. So our aim is to find a balance such that the recommendation quality of inactive user increases and the recommendation quality of active users do not decrease so much. After optimizing, we can see that inactive scores, user score have improved significantly, which ultimately raised the overall recommendation quality. However, one thing to note down is that the recommendation quality for active users have decreased, which is undesirable. So we can control this by using an epsilon variable. So epsilon variable controls a trade-off between the fairness and recommendation quality, and a future aim is to find a balanced epsilon value so that which enhances the active user score without drastically lowering the score of active users. Here we can show the impact of epsilon that is having on the difference in the recommendation quality between active and inactive user. So at the epsilon, when epsilon is equal to 0.0548, we can see that after applying our fairness adjustment algorithm, we can see that the recommendation quality for inactive have increased and active have decreased. But since epsilon is greater than 0, we can see that it hasn't decreased much. So same thing for the NDCG score. So epsilon helps to control the trade-off which is present between the recommendation quality and the fairness. So we can control the epsilon value to find the balance epsilon where the fairness and the recommendation qualities balance. Epsilon controls the trade-off which is present between the fairness and recommendation quality. A lower epsilon value improves the fairness for inactive users, but on the other hand can reduce active users' experience. By adjusting epsilon, we can balance improvements for both inactive without heavily sacrificing the active users' recommendation quality. Our goal is to find an optimal value of epsilon where both groups receive a satisfactory experience. But we can see that when we are decreasing epsilon, so recommendation quality for inactive user increasing, which is good. But on the other hand, the recommendation quality for active user decreasing drastically. So we have to find a middle ground by adjusting the epsilon value. We can balance improvement for inactive users without heavily sacrificing The active user's recommendation quality. A goal is to find this optimum upselling value where we both set of users can receive a satisfactory experience. So to test the robustness of our re-ranking algorithm, we applied it across the various recommendation model, including biased MF, NCF, PMF, and ALS. Results were obtained for biased MF and NCF on datasets with different activity level classification. We also use PMF and ALS rank file for all our datasets, but we didn't use new MF and stamp because they were difficult to compute. And we applied re-ranking to PMF and ALS model, and we observed that our model worked by changing different set of epsilon values. So the main advantage of using algorithm is that the re-ranking algorithm works on different ranking files generated by models and solves the optimization problem, reducing the quality difference between advantage and disadvantage group. And all this is done without directly interacting with the model. This is the main advantage of using algorithm. And we have added all results in graphs in results folder, and which is present in the project directory for your reference. In conclusion, our study shows that the fairness can be integrated into recommendation system with minimal impact on accuracy. By implementing fairness constraints, we improve recommendation quality for inactive and users, achieving a balanced and equitable user experience. Our findings pave the way for more inclusive recommendation system, which can enhance engagement, especially among inactive or disadvantaged users. Looking ahead, we see opportunities to expand the framework to other domains such as content and educational recommendations. We also aim to develop advanced fairness matrices to account for complex user interactions and explore the long-term impact of fairness constraint on user satisfaction. These steps will further refine fairness in recommendation system to meet diverse user needs, which is growing in the current world.